And today, I thank everyone for joining my defense presentation this afternoon with the title as The Structural Origin of Thermal Mechanical Properties and Morphological Behaviors of Semiconducting Polymers. As you might know, our group has a research focus on organic electronics, and there are many facets of it. For example, flexible electronics, wearable, implantable, and thermostable electronics. And specifically, my research is focused on the flexible electronics. And one day, we might be able to use what we learned here and apply it onto some more softer systems like human skin. Before I dive into my talk, I will first begin with some fundamental knowledge about semiconducting polymer, or called conjugated polymer, CPs. When compared with their bulk counterparts or inorganic counterparts, silicon, donor-accepted polymer or conjugated polymers have a lot of advantages like lightweight, solution processability, mechanical flexibility, and high charge carrier mobility. As you can see on the bottom left curve, there is an ongoing effort of synthesizing new conjugated polymers to achieve high mobility. And from the past, we have pentacene and P380 polymers, followed by recently emerged donor-accepted polymer that have much higher charge mobility, and now is approaching crystalline silicon. And shown here is a typical chemical structure of a DPP-based donor-accepted polymer, where donor and acceptor are shown in different color. So from a polymer physics review, we look at this polymer as only two components. One is this rigid polymer backbone, and another is the ultra-soft side chain structure. And this polymer tends to be semi-crystalline. And for the crystalline structure, it's rather complicated. For example, we have charge transport along the polymer backbone direction, and along the backbone, there is alternating donor and acceptor. And the backbone can actually pipeline interact with each other and have this intra-chain charge transport pathway, and charge can hop in between backbone and backbone. Along the vertical direction is the lamellar direction, since polymer side chains are not conductive to electrons. That's why the charge does not transport through that direction. And if we want to maximize the charge carrier mobility, typically we would like to have much better packing phenomenon, as well as better interconnectivity between individual crystallites, so that it can transport in a long-range order. And with this background, let me introduce to you some of the roadmaps for the application of conjugated polymers in the flexible electronics. So we start with the polymer design. You can engineer different types of backbones, the side chain structure. You can also make composite material through physical blending. And followed by that is we are going to introduce a thin film device. So using different fabrication techniques, you can obtain different types of morphology in a thin film. And that morphology is critical in the determination of its final electrical performance, as well as thin film mechanical performance, like elastomodulus. And during the past 4 years of research, I mainly focuses on the structure, thermomechanical property, and morphological relationship. So to summarize my projects, I will list 4 right here. I will start with building this pseudo-freestanding tensile tester to understand the stress-strain behavior of ultra-thin films, as well as understanding their fracture behavior. Followed by that, I try to understand how to control the glass transition temperature for semiconducting polymers and apply the trend we learned to make a predictive model to predict the glass transition for future polymers. I also try to understand the alignment mechanism for the donor-accepted polymer under alignment. And since we have to make these polymers into flexible electronics, and morphology will influence that electrical property. So we need to build this morphology and electrical performance relationship. We also have a paper published together with Dr. Story and Dr. Nazarenko's group, where we built this polymer composite, and it does not only have mechanically tear resistance and self-healing property, it also has self-healable electrical performance. And in this talk, I will separate into 2 topics. The first one is going to be the mechanical and thermal property, and second one is going to be the morphological properties. So for my first project, the main question I want to answer is, how do we engineer a soft and deformable conjugated polymer? And before my PhD, I realized that in the literature, people reported the elastic modulus of conjugated polymer can be hundreds of megapascal, even a few gigapascal. If we look at this modulus diagram, we need to bring it downward so that we can meet with the soft regime. And in order to do that, there are three sub-questions we need to answer. Firstly, how do we quantitatively determine the mechanical and thermal properties? Secondly, how do we build the structure-property relationship? And thirdly, how can we use that relationship to design a predictive model to predict and guide the future engineering of new polymers? So to answer the first question, we need to understand two main challenges in the field. The first one is, how do we understand the thin film mechanics? As we all know, thin film under 100 nanometer will be super fragile. You cannot just transport it into a universal tensile tester. And that's why people tend to measure thin film mechanics on the substrate. For example, nano indentation. You apply an out-of-plane load, like using an indenter, penetrate into the thin film and pulling it out. Now you have a loading and unloading curve. Through that curve, you can extract the stiffness, the hardness, maybe fracture behavior. However, for ultra-thin polymeric thin films, it is super hard to use nano indentation to quantitatively determine the mechanical performance. And why is that? Firstly, there is no stress-strain behavior. We cannot quantify the interaction area very easily. And secondly, there has already been known that there is an intermediate layer between the thin film and air. And in that layer called mobile surface layer, the thermal and mechanical property for that surface layer is very different from the bulk film. So with only top layer mechanical response, you cannot understand the thin film response. The next technique is well applied into the literatures. It's called film on elastomer method. Now, if you want to understand elastic modulus, you simply stretch your PDMS substrate, then transfer the thin film on top of the substrate. Once you release that strain, now you have periodic buckling phenomenon happen on top of the thin film. And the wavelength of the wrinkling is directly correlated with elastic modulus of your film. So now what about we want to measure the fracture strain? You simply use optical microscope to see at which % of strain you achieve some crack formation. And however, again, this technique is very hard to apply to ultra-thin viscoelastic polymers because the wrinkling is very hard to observe, as well as the cracking is hard to observe as well, since these thin films tend to be very transparent. So another challenge is you tend to have a strong binding force between the thin film and elastomer to avoid the delamination. However, that interaction could significantly affect the thin film mechanical and thermal response. That's why we really need is a direct and quantitative measurement of stress-strain behavior for conjugated polymer thin films. Now comes to the second challenge, is how do we determine the TG for these polymers? Previous examples on traditional polymers tend to use bulk measurement, like a bulk DMA or bulk rheological measurement. However, due to the synthetic challenges, we cannot produce that large amount of material. So what about we use a traditional DSC? And as shown on the right hand, this is a typical DSC curve for a DPP polymer. However, now we can only see the side chain TG and melting behavior. And the backbone transition is very smeared inside of these two temperatures. And why is that? The first reason is DSC only provides us very limited amount of cooling rate. Secondly, due to the rigidity of the polymer backbone, the step change of heat capacity upon heating is very limited. So DSC does not have that sensitivity to achieve that step change. And also, since they are semi-crystalline polymer, the amorphous content is very limited. Okay, now how do we tackle on the first challenge? We developed this pseudo-free standing tensile tester, and the step of the fabrication of the film is as follows. So we first establish a two-layer polymer film on top of the substrate, where the first layer is a water-soluble layer, or called sacrificial layer. And on top of that, we have the thin film we want to measure. Now, by laser patterning, we can pattern the dog bone geometry, and upon dipping the dog bone geometry thin film on top into water, the water-soluble layer is going to dissolve, and our polymer is going to be freestanding. With that, let's just connect one linear stage and another load cell on two sides. We can get a real-time force displacement curve, and that can be transferred into a stress-strain curve later. And when compared with a bulk tensile tester, they're actually very similar. We have very high quality data. We can provide multiple types of methods on the thin film testing. We can change strain rate, do stress relaxation, change the environment temperature. Also, we can do the cyclic measurement. Okay, for the second challenge, if we want to tackle on the material amount problem, what we can do is to use this modified DMA measurement, where we can drop cast polymer solution on top of glass fiber. And glass fiber can provide support, and polymer is kind of binder in between. And with only 5 to 10 milligrams of material, we can sufficiently extract the thin film TG response from a traditional DMA test. And as shown here is a typical DMA measurement, where we have two glass transitions be seen. One is around -50 degrees, another is around 25 Celsius degrees. And in the future slides, I will only report the tangent delta TG in the future. If we want to understand the thin film TG, it is also doable. We collaborate with Dr. Zhou in Nanjing University, who has a very specialized technique called acid chip colorimetry. And this is much more sensitive than the traditional DSC and can extract the step change very efficiently. And as you can see here, the TG corresponds well with DMA result. Now to answer the first question, we do have the techniques we use to quantify the thermal and mechanical responses. And now we are ready to test a bunch of conjugated polymer and understand the trend of backbone effect and sidechain effect. So before I talk about my own project, I want to give a few examples of some representative works by other groups. For example, through backbone engineering, Dr. Stingley-Stutzman's group tried to engineer this diplock polymer of P3HT and polyethylene. So they find out with incorporation of more polyethylene in the backbone, the elastic modulus increases, crack onset strain increase as well. However, the increased elastic modulus might not be what we want for a flexible electronics. Dr. Bao's group introduced a different technique. So they introduced conjugation breaker spacers. For example, in this case, C6 and C12. It can sufficiently decrease the backbone rigidity, and the modulus is dropped, crack onset strain is increased. Another similar technique was employed by Dr. Lipomi's group. So by engineering the sidechain of polythiophene, they find out increased sidechain length is going to lower the elastic modulus and improve the crack onset strain. However, there are some shortcomings of these different results, because by using film on elastomer method, their elastic modulus measurement was not comparable from one group to another or from literature to literature, because the strain rate they're using are very different. And that makes a problem. We cannot systematically compare one polymer from another. And also, there is a short understanding on the thermal behavior for the conjugated polymer backbones. And with that, we want to fill in that knowledge gap and provide more systematic study on the quantification of backbone effect as well as sidechain effect. So our first study starts with the understanding of the donor acceptor polymer called DPP-TVT. And here is the structure. So previous results or previous literatures have informed us donor acceptor polymers have super rigid polymer backbone, and that makes them very brittle. That's almost everywhere in the literature. However, when we start to measure this polymer thin films on top of water, we find out it's very viscoelastic. As you can see, the strain rate dependent elastic modulus, the hysteresis, and the plastic strain, well, the modulus is actually super low. It's around 165 megapascal, and when compared with traditional polystyrene, well, only with one 6-ring structure in polystyrene, the modulus is 20 times higher. So why is that? Later, we attributed the low modulus to the low glass transition temperature around room temperature. But now we have another problem. how do we understand this low glass transition? And how do we understand the backbone contribution and side chain contribution? With that in mind, we collaborated with Dr. Garnier in University of Windsor and Dr. Isla here, and we fabricated this systematic study on the backbone thiophenol effect. So thiophenol is very important for semiconductor polymers. People incorporate thiophenol in every semiconductor polymers they made, or most of them, because thiophenol provides a very planar structure. It is also provide conjugation. And shown here, there are two series. The first series have incorporated a larger number of isolated thiophenol as seen by DPPT, T2, and T3. And another set is DPPT, DPPTT, and TTT. For the sake of saving time, I'm only talking about the first three polymers in this talk. So previous literature have suggested if we are incorporating this small ring structure in between a large ring like DPP unit, we can efficiently lower the backbone rigidity. But from our measurement, it seems to be contradictory because we do observe an increase in elastic modulus with incorporation of more thiophenol structure. And later, the increase in elastic modulus were explained by increased glass transition and increased degree of crystallinity. However, we still do not know why the glass transition is increased if the backbone is becoming less rigid. And second observation we made from the stress strain curve here is the crack onset strain. So it turns out the crack onset strain can always achieve like 40%, and it does not seem to be affected by the polymer structure itself. So we engineered polymers with different molecular weight and find out it might be the key for higher deformability. Okay, now to verify the improved glass transition temperature we observed, we use another conjugated polymer system to verify. We collaborate with Dr. Liu in LBNL, where we use a similar concept by introduction of one thiophenol unit into this PAQM polymer. And we find out the TG can be efficiently increased all the way from -18 to 6 Celsius degrees. Okay, so how do we understand it? And it turns out it should be pretty easy if we just use a Fox equation. In the literature, people reported that unsubstituted polythiophene has a TG around 120 Celsius degrees. So just imagine you put that into a low TG polymer, of course the TG is going to increase. And TG for predicted value is actually similar to the measured TG. And now how do we understand the low TG for the DPPT polymer, which is around -4 degrees of Celsius? Well, we know the high TG thiophenol is increasing the TG, then must be the low TG component is dropping the glass transition. So it has to be the side chain effect. Okay, now we identify the origin of low glass transition is from the side chain. So let's take a look at how side chain can efficiently decrease the modulus and glass transition. By using a DPPT3 polymer as a model, we incorporated the C8 side chain onto the thiophenol unit. And with that, we dropped the glass transition temperature for 30 Celsius degrees from 19 to -12 degrees of Celsius. And modulus can be dropped for more than 50% with only 7% increase in side chain content. Okay, now we understand the backbone dynamics can be affected by a high TG thiophenol and low TG side chain structure. But we still do not know how systematically the side chain content will affect the backbone dynamics. And that is the next project. So with that in mind, we designed these following 4 polymers based on DPPT polymer backbone. With increase in side chain length from C2, C6, C8, all the way to C2, C12, C14, we see this stress strain curve where obviously the elastic modulus is dropping with longer polymer side chain length. And secondly, if you see the crack onset strain, again, it does not show obvious structural effect, and we believe molecular weight should be the key. And thirdly, it is kind of weird that the strain hardening behavior at large strain is very different. As shown in the red curve, which representing for the lower, shorter side chain length, the slope seems to be much higher when compared with C2, C12, C14, as shown in the blue curve. Okay, how do we understand this? We have three hypotheses. The first one is different polymers have different Tg, while our experimental temperature was fixed at room temperature. So it might just be T minus Tg effect. The second one is the degree of crystallinity effect, since they are different for different polymers. And third hypothesis is different entanglement density. Okay, let's take a look at the effect of T minus Tg. We can simply warm up the water bath and perform the tensile test under different temperatures through 20 all the way to 50 Celsius degrees. And we saw efficient decrease of elastic modulus with increasing experimental temperature, which is expected. In the meantime, the strain hardening behavior is becoming weaker and weaker. So the temperature does play a very important role here. However, it turns out the slope change here is not as severe as we saw in the curve on the left, because for the longer side chain length, it seems like it's almost flat at higher strain. So let's take a look at the degree of crystallinity effect. We can change the degree of crystallinity by thermal annealing the material at different temperature and not under different time to allow the crystalline domain to become larger and larger. And we find out the strain hardening was not significantly affected by the degree of crystallinity. And this observation agrees with previous studies on traditional polymers. And now we only have another option, which is the degree of entanglement density. And this property will be measured through rheological measurement, and such experiment is undergoing. And we think the temperature and entanglement density both contribute to the different strain hardening behavior. Now let's take a look at the glass transition behavior on the DMA. We find out the Tg decrease with increasing side chain length, which is expected. And the elastic modulus shows a very linear transition versus the glass transition, while the degree of crystallinity does not provide a very important rule in the determination of mechanical response. However, throughout these four polymers, we still cannot build a whole idea of how side chain affect backbone dynamics, because we need a library of polymers with different side chain length to build its library. And it's quite synthetically challenging and experimentally time-consuming. So how do we do it? So we collaborated with our collaborator, Dr. Xia from NDSU. He helped us to build this coarse-grained model, where the backbone is represented by the gray beads, the red beads representing for the branching unit, and the blue beads, or the M value, represent for the number of side chain length. And we find out with increase in side chain length, the Tg drops in a curvy way. So we start with a very sharp decrease in Tg, followed by a very slow decrease. And that can be understood because with more side chain, your polymer is behaving like side chain itself. And if we simulate elastic modulus, we also see the linear relationship between elastic modulus and Tg, since molecular dynamics simulation does not provide crystalline domains. Okay, now we have this curved-like qualitative understanding of how side chain affect Tg. But still, if we want to use this model to predict the glass transition, it seems to be pretty hard. So how do we do it? We consider the side chain fraction is affecting the backbone dynamics. And the Tg of backbone dynamics will be represented by the flexibility of the repeating unit. Okay, so now we need to understand how the side chain is going to affect the flexibility of this repeating unit. And with that in mind, we actually go into the literature and find out this model called mass per flexible bond model, which was previously applied to polycarbonate material. And this model, it simulates the Tg as a linear relationship with this value called m over f. M is the mass of a repeating unit, and f is how many number of flexible bonds inside of this repeating unit. And A and C represent for the intermolecular interaction or steric hindrance, which is now the focus right here. Okay, so let's take a look at this P3BT. I'm going to explain how this model was working. So for the P3BT polymer, there is side chain structure, and we know that each covalent bond of the side chain is very flexible. So from a value of 0 to 1, we gave it a number of 1. So it has full flexibility, while 0 means it does not have any conformational entropy. However, for the covalent bond that is connected to the thiophenene or the thiophenene itself, the conformational entropy is very limited. Okay, let's give it a number of 0.5. With that, the M over F value can be calculated. However, just using this number is not enough. Let's take a look at the glass transition for a series of side chain engineered P380s. With increasing of side chain length, we have P3BT all the way to P3DDT. And in this curve, the TG versus side chain fraction curve, we saw that the trend is very similar to the molecular dynamics simulation results, because the side chain is taking mostly of the polymer itself. Now, let's take this TG and apply it into mass per flexible bond model. It is linear. And with increasing side chain length, TG decrease in a linear fashion, where we successfully use mass per flexible bond model to model the contribution of side chain into the flexibility of the repeating unit. Okay, now we are getting very excited and apply it into the 4 polymer systems we mentioned before. And on the left shows the typical simulated result. The TG is decreasing with side chain fraction. And on the right is a linear fit of these 4 polymers into mass per flexible bond model. If we add 2 more polymers with intermediate side chain, it's still valid and make this linear fitting to have a very high confidence of 98%. Okay, now we start to worry. Is the model we are choosing very simple, or the polymer system we are choosing too simple? Now we have to apply it into another polymer system to prove the generality of this model. And previously I mentioned this PDPPT2 polymer with 1 more thiophenene in the polymer backbone. Let's put more side chains on it. Okay, now from C2, C6, C8 all the way to C2, C12, C14, the TG decreased all the way from 65 Celsius degrees to 1 Celsius degrees. And that can be fitted into a mass per flexible bond model very nicely, just like PDPPT. And now we can say we can have a very nice empirical model to predict the TG for these 2 types of polymers. So now to answer the third question, can we build molecular design rules for the future engineering? Well, yes, to some degree. We can simulate DPPT polymer, DPPT2 polymer. But for another polymer system with different polymer backbone, if we want to use this model, we might have to synthesize 4 or 5 polymer structures with different side chain length. And that is not efficient at all. Okay, how do we figure out that problem? Now we are collaborating with the simulation group and try to combine the simulated result with our experimental measured result. And by using all atomistic modeling, we hope that in the future, if you draw a chemical structure on the paper, we will be able to tell you what's the TG for that. Okay, now let's transition to the second project. We understand the donor acceptor polymers are pretty viscoelastic, has low modulus, can have low glass transition temperature. But we need to apply these polymers into flexible electronics. We need to strand it and let it function like itself. So how do we understand the structure, morphology, and charge carrier mobility relationship during tensile alignment? And that's the aim for our project. And to successfully understand this relationship, we need to answer the following 3 questions. Firstly, we need to identify different components in the thin film morphology and what are the different alignment mechanisms for these different components. And secondly, what is the role of backbone and side chain during tensile alignment? Since they are covalent bonded, previously there is a lack of instrumental method to separate their contribution very efficiently. And thirdly, how do we understand the morphology and electrical property relationship? Okay, to start with, I want to introduce some of the complexity in the structure and morphology of these donor acceptor polymers. So polyethylene, a traditional polymer, typically has a persistence length of around 7 to 9 angstroms, while P3HT is 3 times more rigid in the backbone. and donor-accepted polymers is 6 times more rigid than P3HT. That's why in the thin film morphology, they are very different. For example, polyethylene and P3HT can sufficiently have this chain folding behavior in the crystalline domain. And that's why it can form this semi-crystalline morphology. However, for these super rigid donor-accepted polymers, it turns out chain folding is not that efficient, and in the local crystallite, it's very different. For example, what's shown here is different clusters of polymer chains are peptide interact with each other, as shown in the red regions. And in the crystalline structure, the packing phenomenon is very complicated as well. So we have 3 directions of interest. The first direction is along the polymer backbone, which we call 001, and that is composed of alternating donor and acceptors. The second direction is the B-axis here. It's called pi-pi stacking and represented by this 010 peak. The third direction, or the A-axis, you can see it is side chain packing, or we call it as lamella packing. And this is very different from traditional polyethylene as well. So to understand how this complicated morphology align under tensile alignment is very complicated. For example, people have shown that the alignment mechanism for P3HT by using different techniques. By using AFM, they can look at the thin film surface morphology. As seen in the bottom left, you can see that thin film morphology will be different from 0% strength to 150% strength. Basically, it's more elongated. And by using GWAX, we can look at molecular packing of crystallites. If we choose different angles between the incident X-ray and the polymer and aligned thin film, we will be able to understand how is the crystallite aligned along different directions. Thirdly, by using polarized UV-Vis, which looks at the intermolecular aggregation, it will help us to understand the chain alignment of averaged polymer chains. And that is obtained from the absorbed intensity when the polymer thin film is parallel versus perpendicular. So as we talked about, P3HT is semi-crystalline, and while donor-accepted polymer is kind of disordered aggregated structure. So now there has not been any study on the chain alignment mechanism for donor-accepted polymers, and that's the origin of our project here. So in order to design such experiments, we do need to align thin films and provide different degree of alignment. And as shown on the left, you already seen this, is how is the stress-strain behavior different for different types of DPP polymers. And in this case, I will start from one polymer, DPPT C2, C8, C10, or the yellow curve. And from that, I will explain how is the chain alignment mechanism like. Then I will discuss the side chain effect. Okay, shown in the middle is how we prepare our samples. We align the thin film on top of water, then transfer it onto a hollow washer. By putting the hollow washer in between the incident light and the detector, we can change the type of light to understand the different components inside of the thin film. Okay, now let's talk about different types of light. By using scattering technique, we can look at is the crystalline region. And hard X-ray is widely applied in the past literatures, and people are looking at how the crystalline have the lamella packing and lamella rotation phenomena during alignment. However, by talking about lamella, it is composed of both the backbone and the side chain. However, it's very difficult to separate from these two because they are very similar in the structure. And recently, there is a new technique called tender X-ray scattering, which can change the energy of X-ray to around 2.8 kilo eV. And that allows only the sulfur atom along the polymer backbone to absorb this X-ray and scatter. So now we find a contrast between the backbone and side chain, which is the sulfur atom along the polymer backbone. And by using this technique, we were able to look at the backbone packing inside of these crystallites. Next, by using spectroscopy technique, which is a technique that does not only looking at crystalline domain, but also looking at amorphous domain. So next NFS, or near-edge X-ray absorption spectroscopy, provide a method which, by using a polarized soft X-ray, we can see the backbone rotation during the chain alignment. By using polarized UV vis, just like the P3HT study, we can look at the average alignment of all polymer chains. And in order to quantify the degree of alignment, we will be able to use this 2D Hermann's orientation parameter, or F value. If F is equal to 1, it means the chain orientation and the direction of interest are parallel to each other. If F value is equal to 0, it means it's basically an isotropic scattering. Okay, so by using scattering technique, we can do the pool figure analysis on a specific peak, and that is telling us how is the anisotropy like for that peak. And by using spectroscopy technique, we can provide a dichroic ratio from the absorption when the film is parallel versus perpendicular, and obtain this F value using this simple equation. So now let's take a look at the hard X-ray scattering first, which looks at the lamellar rotation phenomenon. And on the right shows two representative GWAX to the image, X-ray scattering to the images. One is 0% strand, and another is 0.59% strand. And as you can see, for the 100 peak, obviously, after alignment, there is anisotropy, and the 0.010 peak shows anisotropy as well, together with amorphous peak. While we also observe the emergence of two new peaks, which is our 001 and 001 prime, representing for the backbone scattering peak. And from this 2D wax image, we can extract some necessary information. For example, what are the crystalloids like after being deformed? And shown on the bottom left is 4 types of crystalloids that we think that will be existing in the thin film. And more importantly, let's take a look at the orientation parameter evolution upon strain. So as we talked about, 100 peak is the lamellar rotation peak, and delta F value reaches 0.6 after strain, which means this rotation phenomenon is very efficient in these polymer thin films. And that is understandable because your crystalloids are aligned along the strain direction. However, the 010 peak does not seem to be aligned to a similar degree as 100 peak. And why is that? It seems to be strange, because if you imagine if a crystal does not change its shape before and after alignment, then along 3 directions, it should show very similar degree of alignment. But now, the delta F value is only 1/3 of the 100 peak. And we hypothesize that it's because during the crystalline orientation, there is backbone slippage between the pi-pi interaction. Since the pi-pi interaction between backbone is pretty weak, so the backbone can be extracted out of the crystalline domain. That's our hypothesis, and we will prove it later. Okay, another contribution we think we make to the field is the determination of the amorphous peak. So previously in the literature, people kind of have different opinions on the origin of amorphous peak. Some people said it's coming from randomly oriented side chain. Some people said it's coming from randomly oriented polymer pi-pi interaction. And our observation seems to favor the second explanation, because we saw a delta F value exactly the same from the 010 peak. Okay, now comes to the interesting part. The tender X-ray scattering is giving us the backbone scattering signal in the crystallite. And as I talked about, we need to choose an energy that sulfur atom absorbs. And in the figure on the right, the sulfur edge fluorescence yield, what we can identify is 2 energies that 2.47 keV representing from the onset of the absorption, and 2.478 represent for the maximum absorption from sulfur. So let's take a look at the orientation parameter under these 2 different energies. While 2.47 keV give us delta F value of 0.6, which is exactly the same with hard X-ray. And that is understandable because at this energy, we are looking at the entire lamellar structure. However, at 2.478 keV, the degree of alignment is significantly smaller when compared with that F equal to 0.6. And why is that? And now we think we proved the backbone slippage mechanism we brought out before. Because when the crystallite is aligned, the backbone alignment was smaller than the degree of alignment of the crystallite itself. So the backbone slippage does not only happen from the pi-pi interaction, but also happen between lamella and the lamella due to the van der Waals force during the side chains, which is pretty weak. Okay, now the third observation we make is the backbone rotation mechanism. And next FS help us to look at the absorption orbital for the 1s2 pi star orbital. So basically, we are looking at the following two modes of rotation, mode 1 and mode 2 here, where mode 1 meaning your polymer backbone is rotating from vertical to horizontal, where mode 2 is simply a flip. Okay, the delta F value for this mechanism is equal to 0.4, which means it's very efficient in the thin film deformation. Now it comes to the polarized UV-Vis. And from the absorption at 0, peak, we were able to compare the dichroic ratio, or we were able to measure dichroic ratio for parallel versus perpendicular direction, and the delta F value is calculated to be around 0.14. And this number is significantly smaller than all the numbers we've reported previously. So we saw the backbone alignment in the crystallite is equal to 0.423, and this is equal to 0.14. So it suggested us that the slippage of amorphous chains are more significant than slippage of backbone. And that can be understood because in the crystalline domain, you still have this pi-pi interaction as the impedance force. Okay, now summarize the chain alignment mechanism for donor acceptor polymers. For different regions, they are very different from each other. From crystalline rotation, from a crystalline domain, you can see the rotation behavior. You can see the backbone being extracted out of the crystallite. From the all polymer chains, you can see the backbone rotation as well as the alignment of the average polymer chain is very limited. So now you might wonder, okay, what's going to be the effect of this morphological transition on the thin film electrical performance? And our collaborator, Dr. Cho from NTUST, helped us to perform this kind of measurement by fabricating OFAT devices. And as you can see here, along the charge transport versus perpendicular to the charge transport direction, we do not see any difference in the mobility value under strain. So which means the charge transport is as efficient as the non-strain state. And there is no increase in the alignment when the strain direction is parallel to the mobility direction. And that can be explained by the decrease, the crystallographic slip, as well as the limited degree of alignment in the polymer thin films. And this actually explains another observation from a different publication. So previously, people used this thin film unelastable method to align the thin film and say that for IDT-BT donor acceptor polymer, there is no enhancement in the mobility value along the charge transport direction neither, as shown in the blue dots. And in the red dots representing for a more brittle material, DPBTT, where mobility is actually dropping. And from the bottom, we do not see anisotropy value neither. However, previous publication failed to explain the origin of that behavior, and our observation proved it. Now let's talk about the effect of side chains, as I promised. So based on these 4 different techniques I talked about, in the top 2 curves I showed is how the crystalline orientation is different for different side chain engineered DPP polymers. And the answer is the side chain length does not necessarily change the alignment mechanism of crystalline domains. It still have rotation, it still have backbone extraction to a similar degree. However, in terms of spectroscopy technique, we saw some difference. From NextFS, we find out larger size of the side chain is actually restricting the backbone to be rotated and that can be explained because when the backbone is rotating, the large steric hindrance from larger side chains is stopping it from further being rotated. And from UVVs, we identified a little bit of increase in the degree of alignment for average polymer chains when we increase the side chain length. That could come from the more mobile polymer backbones for longer side chain polymers. So to summarize this project, we successfully identified different mechanisms for different components. We also disentangled the role of backbone and side chain of the crystalline orientation. We also identified the alignment mechanism effect on the thin film electrical performance. So in conclusion, I hope I showed you a coherent study on the structure, thermomechanical property, and electrical morphology relationship for conjugated polymer thin films. And we showed the linear region where TG and elastic modulus play a very important role, the plastic region where chain alignment happens, and also I have an ongoing effort to understand the fracture behavior of these donor acceptor polymers. So with that, I want to acknowledge a lot of people here, all my committee members, my mentor, Dr. Gu, who provided a lot of support during the past 4 years of my research. He guided me through engineering my project, writing the proposal, writing my documents, performing experiments, and tutoring undergrads. So every single step that allowed me to be an independent researcher, he was there to help me. I also want to acknowledge Dr. Morgan to allow me to get in this department. I had never regretted that decision ever since then. I want to thank Dr. Islay and Dr. Nazarenko for your collaborations and all the group members, including Lithan, Jasmine, Eric, and Bebe. I want to thank Dr. Patton for nominating me as the Graduate Student Hall of Fame, as well as your leadership in the past pandemic. I also want to thank all the faculty members. A lot of faculty members have provided me access to their lab, like Dr. Wiggins allowed me to use the DMA. And I want to thank all the good research group who has been wonderful colleagues in the past years. And the founding members, Dakota, I think is in the audience, Daniel, and all the new guys, thank you for being there. I want to thank the first year class, my friends and families as well. So lastly, I want to thank all my collaborations out of USM. There are many of them, as well as the funding agencies. So with that, thank you very much. I'd like to answer any questions you might have.